Hello, everybody, and welcome to our webinar dedicated to the FX50 cameras. I'm glad to have you here with me tonight in our studio. As you can see here, we have a mock-up device of the FX50, and I would like really to warmly welcome you here in our studio, you who are just interested in the device, all our potential customers, our existing customer partners, and also competitors. So, welcome. Here you can see the user interface for this webinar. As you can see on the right-hand side, there is an icon where it's written chat. There you can write all your questions. We will read them from there. At the beginning, there will be an introduction presentation held by myself. It's going to last about 20 minutes, more or less. And then there will be some time dedicated as a Q&A session. For this webinar, we will be actually 2 persons. So here, actually, the presentation can start. And we will just go along this way. So here is a presentation. MWIR stands for Mid-Wave Infrared and Spectroscopy Made Easy. It is actually our motivation in this hyperspectral community and for our partners to make hyperspectral easy, because it's not that difficult, actually. So we are 2 to make this happen tonight. There is me, Mathieu. I'm working as Specim since 9 years. I'm now working as a senior application specialist. And there is also Jeff Oleski, who is based in New Jersey, has been working with us since 1.5 years. So maybe, Jeff, you could say hello.
Yeah, hello, everyone. I'll be jumping in at the end of your presentation to go over the questions, and we can have a discussion then. Okay.
So then we will start to go with a general presentation about Specim. Just for your information, remember that already this year we hold 2 Q&A sessions. You could see them on YouTube, and there I explain also who we are and different type of applications. The first webinar was dedicated about the food industry. The second one was dedicated about waste recycling. This one is dedicated about FX50. So first about us. We are the world leader manufacturer and system provider in the field of hyperspectral imaging in the whole world. We have been established in 1995, and Specim is a spin-off of VTT, which is a Finnish National Research Center. It started with 3 guys who are still working with us. And now we are about 70 employees. We are mostly based in Oulu, northern Finland. We have as well an office in Helsinki, another one in Shanghai, and also 2 nowadays in the United States. We have one in New Jersey with Jeff, and we also have Martin in Detroit. So basically, what is spectral imaging? You know, every material, they are made of different molecules. Each molecule, they are made of different atoms. And then, depending how they are arranged, bound together, when we send an electromagnetic wave, like simply the light, depending on the molecule and the structure of the material, the compounds, basically some of the light will be absorbed, sometimes will be reflected, will be also just passing through, and this can be measured. It could also emit, of course, and this can be measured, and this is actually spectroscopy. So basically, we can measure for each material which kind of wavelengths is reflected, absorbed, transmitted, or even emitted. Based on that, it's possible to make some recognition of different types of materials. That's why hyperspectral imaging could be used to identify different types of material, for instance, for the plastic recycling, or just in recycling in general, but also for the food industry to detect some contaminants, and also to quantify some really important parameters, just as the moisture, protein content, different things like this. What is hyperspectral imaging? I was explaining what is actually spectroscopy. You remember, spectroscopy is a measure of the intensity for each wavelength of how the light is reflected or absorbed or emitted by an object. Hyperspectral imaging is a combination of an image and also spectroscopy. So here on this slide, you could see, for instance, an object. Because we're in the digital world, we actually have pixels out of it, looks like a grid. And the way we represent a hyperspectral image is like a cube. So for each of the pixels, it's possible to see for each wavelength how the light is reflected and absorbed. So it's a combination of spectroscopy and also imaging. So that means you could also see homogeneity and you could point out where different objects are located. This is how our camera looks like. This is, for instance, the FX10. The FX10 is between 400 and 1000 nanometers. This is not the topic for tonight. Tonight we speak about a bigger guy, which is here, which is in the mid-wave infrared. But they are working in the same fashion. So basically, when you are making hyperspectral imaging, you need to have an illumination like this, and the camera looking at the top. And because we are making only line scan devices, which are really suitable for industrial environment, there is a conveyor belt where the samples or what you want to sort is located. Then line after line, like this, you can make an image, or for each pixel, you can actually find what is made of what, working a bit as a fingerprint. So for instance, you can see on this picture, there is a spectrum, a blue one, for instance, here related to one material, and there is an orange one related to another material. You can build a spectral library where you teach a model, this is a spectral signature of A, this is a spectral signature of B, and when you put under the camera a sample that you do not necessarily know, then with statistical model, it is possible to identify, is it A or is it B? If it is no one of those, then it is a third class. But this is how it is working. And because those are line scan devices, for each pixels of the line, you have independent hyperspectral information. How to produce a hyperspectral image, especially with our camera? First of all, it looks really difficult, but then actually it is very simple. At the front hand of the camera, there is a lens. In this camera, it is located here. The lens, and watch out that it doesn't fall down, right, is okay. The front lens here is only here to define the field of view. So we have different one for different camera to match different type of requirements. It could look with a more or less narrow angle. Then there is an entrance slit. The entrance slit is here so that actually the camera can see only through a line. The light is entering the slit and then passing through a spectrograph. So spectrograph deviates the light depending on the wavelength. For instance, here, the blue part of the light, so let's say with the shortest wavelength, is deviated downwards, whereas the red part of the light is deviated upward. And this is done or projected over a 2D matrix detector. And then line after line is possible to reconstruct like this, a hyperspectral cube. You could see actually that on the 2D detector, there is a spatial axis and a spectral axis. All our cameras are working as the same fashion. They are all built following the same model. Here, we decided to work with push broom method. Push broom meaning that they are all line scan device and then you can reconstruct the cube like this. Why do we do that? You remember when I was talking about what you need to make a hyperspectral system? You need some illumination. Talking about the illumination, it is much easier to control it and have it homogeneous over a line than to have it over an area, for example. That's one thing. Then, because you can concentrate the light over a line, it could be much more intense. That means that you could have a shorter integration time than, for instance, with an area camera, shorter integration time, faster frame rate for faster industrial application or faster measurement simply with that. Also, the good point with push broom device is that it can be used in many types of environment. It could be used in a laboratory, using, for instance, a scanner or using a conveyor belt. It could be used as well in industrial environment, meaning over a conveyor belt for real-time sorting. And it can also be used on the field and in airborne platform. That means that the same device can be used in many purposes for many types of activities. At Specim, we are actually building hyperspectral camera from the visible spectral range, starting at 400 nanometers up to 12 micrometers, which is the long wave infrared. And in between, there is everything you need. There is a visible, which is between 400 and 800 nanometers, very suitable for color measurements. There is also the VNIR, NIR for near infrared, which is between 400 and 1000 nanometers. This one is more suitable, for instance, for vegetation or phenotyping. We also have the NIR, which is between 900 and 1700 nanometers. Then the SWIR camera for shortwave infrared, which is between 1000 and 2500 nanometers. And then we can go even further. Here we are talking about the MWIR camera, which is here between 2.7 and 5.3 micrometers. And finally, the long wave infrared between 8 and 12 micrometers. As a rule of thumb, we consider that thermal infrared starts beyond 3 micrometers. So now we are really talking about a thermal hyperspectral camera. In practice, I would say that it starts already at 2 micrometers. We start to see already influences of temperature on hyperspectral signal above 2000 nanometers. But here, it is fully a thermal hyperspectral cameras. Here about the FX series. I'm sure that many of you have heard already about the FX cameras. We started about, let me think, 4 years ago, 4 years and a half ago, we started with the FX10. Then after that, 6 months later, we came with the FX17. And in order to complete with the FX families, it's not over yet, but we are now going with the FX50, which is from 2.7 to 5.3 micrometers. This one was launched, I would say, about 2 years ago, or a year ago, actually. It was a year ago. Those cameras, they have been designed to match actually the need for industrial player, for industrial partner, integrators, and OEM. Why is that? We have those one. We try to have a complete family to overcome as many applications as possible. For instance, here, the FX10, which is, as I say, between 400 and 1000 nanometers, very suitable for color measurements, but also everything related for vegetation analysis. We also have here the FX17, which is between 900 and 1700 nanometers, and then the big brother or the big sister, depending on how you see it, between 2.7 and 5.3 micrometers. This one is really dedicated for the industry. We had another one before, another MWIR camera, but it was not as well finished or designed as the current device that we are having here. And I will explain why this one is more finished, more robust, more ready for the industry. First of all, as it is a member of the FX family, all the devices, they have actually the same output in terms of wavelengths. Inside the camera, there is a firmware, or there is a capability to take the data and to make an automatic image enhancement, meaning that all the device will get as an output the same spectral calibration. That means that if you build a model with one device, you can swap the camera with another one, and the model will still be valid as the spectral calibration will be exactly the same one. Also, this automatic image enhancement allows that the cameras, the output is free of keystone and of smile, which are spatial and also spectral aberration. So this applies as well for the FX50. Also, A key parameter of those cameras is the capability of picking up only the wavelengths which are relevant for your application. Let's take a typical example. You want to work in an application where with the FX50, you don't need the full spectrum. Remember, from 2.7 to 5.3 micrometers. But you know that what you want to do, you need to have only a camera where you get data between 3.3, for example, or 3.5 micrometers. It is possible for you to disregard what you had before and also beyond the spectral range of interest. Then, if you have less data, it means that it is less greedy in terms of processing power, less data, less power, but also the camera could be faster because less data are transmitted and need to be read. So as an example here, if you take 3 specific ROIs, which is about 4 bands, the camera has a full frame rate, as a maximum speed can be up to 1,200 frames per second, which is quite fast already. Frame per second, remember, line per second. Also, if you're interested in still reading the full spectral range between 2.7 and 5.3 with the 154 bands, the maximum frame rate is about 377 frames per second, let's say 370 frames per second. Having said that, there is an important parameter here that you need to take into account. What is really important and have a significant impact on the frame rate of the camera, it is the distance between the first and the last band that you want to read, regardless the amount of bands. That has a really, really high impact. About the stability, you remember I told you before we had another camera and it was not as well finished, let's say as well designed. A key parameter that we did not have before and that we have included with this device now, it is the stability. As you can see, it is fully cased. Even the optics, it's here, is not outside. It's not like the FX10, neither the FX17. And here comes the fact that now we are talking about a thermal hyperspectral camera. As it is a thermal hyperspectral camera, as we are looking for wavelengths within the thermal infrared, as you can imagine, if the temperature of the optics change, its emission change, and this will have an impact on the data you will receive from the camera. So to overcome this issue, we decided to stabilize everything, even the optics. The detector, of course, it is a INSB, which is cooled down at about 80 Kelvin with a Stirling cooler. But the optics in there is stabilized at 20 degrees centigrade, 20 Celsius. Here, it is always the same. So that means that when you close the shutter, when you take the dark reference, there is a shutter in that camera. So when you close the shutter to take the dark reference, you know that this dark reference is valid because the temperature of the optic will not change. If you will have a change of even 1 or 2 degrees, then this dark reference will not be valid anymore. And this is an important thing here that we are adding with this camera. It is stabilized the detector, but also the full optics. It's a plug and play. It's what I was explaining. All our FX cameras, they have as an output the similar spectral calibration, the similar wavelengths. So that means that they are somehow hot swappable from one device to another one. When you build a model, it can be used with the next camera and so on. So this is an important feature because we understand that for some application, having the capability of using one model and dispatch it to many different machines is really a key feature here. So we have it. Here you can see the data sheet of our 3 FX family member. I'm not going to go through the FX10 and the FX17. You can go through, we will go through quickly the one of the FX50, as I was explaining, between 2.3 and 2.7 and 5.3 micrometers with 154 bands, which is giving a sampling of about 16 nanometers. Here, we recommend to use it with a binning time 2 in the spectral direction, and actually this 16 nanometers it is when already applying the ×2 spectral binning. It has 640 spatial pixel per line. And the maximum frame rate, we already mentioned about it, about 370, 380 frames per second. We have developed 3 types of lens to match different type of application and different type of requirement in terms of width for the conveyor belt. We have 24 degrees, 45, also 60 degrees. The optics is a rather good quality, transmitting really well with the f number of 2.0, and notice the superb signal to noise ratio, which is 1,600 to 1. There is only one type of interface of output for this camera, which is GIGI, meaning that this camera is compatible with GIGI vision. You know the size. It's I will not say it's a shoes box, but it's about the same size for 7 kilo. And as all our FX camera, the shutter is integrated for easy capture of the dark reference. Now, when we are talking about thermal infrared, the camera is one thing. But you remember illumination was another important parameter in your hyperspectral system. And we are able to provide you with our thermal illumination. We have one designed by Specim, and here you can see how it looks like. Basically, it's a pair, it's 2 elements. It's about 1 meter long with a rod, which is making the light, which is 80 centimeter long, and we consider the effective area, it's about 60 centimeter long. There are some other ones available on the market, but this one is the one we made with our own design. And you see the way it has been made. So you have the rod, and then there are some collimated mirror, which are actually gold coated, so that the 2 elements, they are focusing on a single line like this. It's really well focused. You could see how it is made. If I am myself the illumination somehow, that's the rod, you can see that the mirror looking like this, it's almost like having a cylinder. You have the direct illumination from the hot rod and also the reflection from the mirror. So that means that this illumination is quite efficient. And when we are using the FX50 with our illumination, typical integration time is about 0.6 milliseconds, 0.6, 0.8 milliseconds. That means that the camera can be run in a really fast acquisition rate. As mentioned, this camera is a line scan device. Since it's a line scan device, if the object is not moving, you will see always the same line of the object. It's not really good to make an image. So at Specim, we have designed and we are making different type of scanners. The first one, which is here, it is our 100 by 50 scanner. You could see how it looks like 100 by 50 wide, means that you can put samples as large as 100 by 50 centimeters. It includes illumination, as you can see on the drawing. You can see as well on the left-hand side a picture where the camera is looking between the 2 illumination elements. And this one is very suitable to measure like a sample in your laboratory, for example. So illumination and white reference is also included. Here about the white reference, we are not talking anymore about spectraclone. We are talking about an aluminum bar which has been sandblasted for better diffusion. So here, this is what we have for the lab. It could be used as well on our Sisu rock. Sisu rock for geological application. On Sisu rock, up to 3 cameras can be put inside to image samples and drill core at the same time. One of those cameras could be a FX50 with illumination. To give an idea about the size of the boy here, from the left to the right, it's about 4 meters, something like this, 4 to 5 meters, and it's about 2.5 meters high, just to give an idea. It's not a small boy, it's a big one. It's possible also to use our camera on the field with a rotary scanner. This is how it looks like. Basically, the camera is mounted at the top of a tripod with a rotary scanner. The camera is looking sideways like this, and then, by rotating, line after line, it's possible to reconstruct a hyperspectral cube. We have 2 ways of doing that. Here, you can see the camera without any black body in front of it. we also have the possibility to mount a dual calibration black body in front of the camera for radiometric calibration all the time for every data analysis, for every data acquisition. But you know, using the camera outside is not easy for one reason, especially for this spectral range. And here, if I'm showing this graph about atmospheric absorption, is to explain and to highlight that this camera cannot really be used for airborne platform, for airborne imaging, for remote sensing. Why is that? Look at the atmospheric absorption parameter. Actually here, I will use a bit the pen. We are in the spectral range between 2.7, so 1, 2, so starting somewhere here, and 5.3. So 1, 2, 1, 2, 3, 4, 5. So we are ending somewhere here. As you can see, the atmosphere absorbs really significantly here, CO2 very significantly here. So that means there is not that much signal which is left when you are dealing with remote sensing, because in remote sensing, the illumination is actually provided by the sun. So if between the light source and the instrument or the sample, there is basically no light which is coming, there is almost nothing which is reflected either. So that means here, this is not really easy. And there is another parameter to take into account. In this spectral range, at the beginning, between 2.7 and 3 micrometers, the reflection from the sun, from the sample, is dominating the emission of the sample. This is true for ambient temperature samples. But on the other hand of the spectrum, when you are close to 5 micrometers, the emission, the thermal emission of the sample is dominating the reflection from the sun. So that means in terms of data processing for remote sensing, that would be a nightmare. So that's why actually we don't use this camera, or we don't know really application which will require this camera for remote sensing. For thermal imaging, remote sensing, the long wave infrared between 8 and 12 micrometers would be more suitable. Then I will explain and I will present few applications where we know that this camera has been used quite successfully. Those measurements and those analyses has been run in Specim. First, this camera has a good thing that it can separate the black plastic from each other. You know, recycling is important politically, but also there are a lot of decisions taken for that, but also it has to be environmental friendly. We have to live on our single Earth. It's important. We cannot escape from it. So we have to keep it clean as much as possible. We are using plastics, and those needs to be recycled. With the FX50, it is now possible to sort different type of black plastic. And here's an example with ABS, PE, and PS. This camera offers the capability to separate those, and some other ones as well. Like I tested PA, I tested POM, yeah, many of those. But the good thing also, because it's not blind in the thermal infrared for black plastic, it's also not blind when the plastic, they are not black. It works also really well where samples are, for example, here, white. I measured as well samples made of PE, ABS, PVC, PS, and so on. And it was really possible to sort them. And you could see actually this image is not Photoshop because you can see the sorting is not perfect. But I mean, still, it shows a really high capability of this camera for plastic, black, but also regardless their coloration. Another application where we think there is a high potential, and we are having some partner and customer using the camera for this, it is for geological application. There is not that much yet which is known about the use of this wavelength for geology or in general for many applications, but it seems that this camera is really relevant for carbonate, quartz, and sulfate. Here, we feel there is a high potential, so that's why we decided to have the possibility to have a module for our Sisu rock with the FX50 included in that. Another application could be for the steel industry. This time the camera will work more in the reflection mode, or in the emission mode, sorry. And it's possible to monitor different type of oxides, for instance, and also to see if there is water or oil at the top of hot stacks. That could be another field of application. We tried also on tires. To make tires, a lot of gums are needed, and they have to be located at the right place with the right compounds. And the FX50 could be suitable to map this to detect if the mixture and the composition is correct at the right place. So we decided to test on tires. Those ones were pretty old, so it did not provide the best spectral response, but on new ones, it's much nicer. But already here, you could see the spectral signature, and you could see the signal is not flat. Be aware that only the FX50 will be suitable for this application, this spectral range, because tires or the gum is full of atoms of carbon within the polymers. That's why with the SWIR camera, for instance, no signal could be seen. You really have to go beyond 2.7 micrometers. Here is an example of the utilization of this camera outside. It's what I was explaining. Camera was used on a rotary scanner. The black body was not attached to the camera just in front of it, but it was part of the scene. You could see actually the black body there, which is red with a dark square at the middle. Okay, this is a type of application. It could be used for military purpose. That could be used for monitoring purpose. That's an example of image we could get with the FX50 outside. Surprisingly, as you can see, quite a lot of signal can be seen in the thermal infrared here between 2.7 and 5.3. It was a cold sky. It was pretty black. And finally, as a last application, once I had a customer asking about the utilization of MWIR spectral range for art investigation. To me, first, it was a bit funny, telling that, okay, you have to be careful because we're in the thermal infrared. They say, yes, okay, we can try using our 100 by 50 scanner. We put a different type of paintings under the camera like this, and we measured. First of all, we measured, does it heat up a lot, the sample, or not? Because if you start to put a masterpiece, you don't want it to burn right away. So we measured, and with our illumination, with the scanner moving at about 20 centimeters per second, which is easily doable with our system, we noticed that the temperature of the painting was rising of only 3 to 4 degrees when it was passing underneath. So that's not much. So then, once we tested that, we started to put some real paintings underneath. I cannot show them, but I can show actually where there was a test of different type of pigments. And as you can see there are really clear differences in the mid-wave infrared for different type of pigments. And that was a nice findings. So basically, I'm over with my introduction. It was a bit longer than 20 minutes. Sorry for that. So now I'm going to give the hand to Jeff, and we are going to go through your questions. Thank you. So Jeff, please, stage is yours.
Yeah, and thank you, Mathieu. That was very good. Great overview, and we got a lot of really good questions. Let me find the best first one here. A couple of questions about software came in. What kind of software, pre-processing software, are we using in the camera, and what would you recommend people do in order to process their data and get the images that you were showing?
Okay, so in terms of software, first of all, if you buy our camera with a scanner, there will be Lumo Scanner, which is our acquisition software, which is included with the system. So there you will have the capability to record the image. The image which will be recorded, they will be raw, or they could also be saved in reflectance. Reflectance, it means that you compare for each of the wavelengths how the light is actually reflected. So we have a kind of plugin for that. So here it's possible to get that. But if you want to incorporate this camera within your industrial environment, then you want to have the capability of having either a turnkey solution with an existing software, or you want to have the capability of coding yourself. So about existing software, we know there is a company in Germany called LuxFlux which is developing the compatibility with our camera for acquisition and also real-time data processing. On the other hand, if you want to make everything by yourself, it's possible. There are different approaches. This camera is GenieCam compliance, the GigiVision compliance, sorry. It has a JSON protocol, also compliance, that we can provide. And because it's part of our camera, we are now working to make it fully compatible with our software development kit. And this is going to be released at the end of this month. So basically, there are many approaches which are doable for that. In terms of processing, when I was showing those data processing, you know, for black plastic, but also white plastic sortings, I was making the normalization. And then after that, Savitsky-Golay, for example, a derivative, no derivative, different region of interest, spectrally speaking, and then typically a PLSDA algorithm for the sorting.
Great. Another question we got is, are we able to run samples for customers? Would they be able to send us samples to examine, to image, and then provide with them some information that we can get from samples that they provide?
Well, basically, we are not a service provider. So we accept samples for a feasibility study. For example, if there is a potential OEM integrator or partner who is wondering, okay, we believe we are making sorting machine, we believe in your technology, but we want to make a test first. Yes, typically for this type of demand, we accept a first feasibility study, which is free of charge. But then we need to assess if there is a potential behind. As I say, we are not a service provider. But yes, we can provide this type of feasibility study.
Could we provide documentation with a more precise description of the pre-processing that's done in the camera?
You mean about the automatic enhancements? Yes, about the keystone correction, about the smile, and so on. Well, it's a kind of speaking proprietary here. We have, when you buy the camera, you can enable or disable it, but we don't give too much details how it is done. You know, it's part of our know-how. We don't want to give everything like this.
Okay, before the next question, I also want to note we added a poll to the right side. So if you look at where the chat box is, just below chat, there is a poll going on. It looks like a lot of people have voted. And it actually looks like most people are writing other. So the question is, what is your application area? Recycling, food, geology, and other. As of right now, 2/3 of everyone here is saying other. So it would be great if you could be a little more specific and maybe write in the chat box what your application space is. And if you have a question regarding that in particular, that would be great. Moving on to another question for now. Are there illumination fibers or dyes that you can add by wool textiles so that you can sort with this camera? So, yeah, so illumination fibers or dyes. So something to add to the sample, I guess, to make it visible. Is that how you interpret that?
Yeah, could it be that kind of fluorescence or somehow? I'm not sure to really get the question here.
Yeah, I mean, to go back to the illumination, I mean, you discussed the illumination for the mid-wave infrared. It's thermal, obviously.
Yeah.
How does that compare to the FX10 and FX17 that you showed?
That's actually interesting because, okay, for the wavelengths, which are between 400 and let's go up to 2,500 nanometers, what is available now? You could use LEDs. It starts to have some available, especially covering the range between 400 and 1,700 nanometers. But I don't know any LED illumination available for the mid-wave infrared. I have never heard about that one.
Right.
Then between 400 and 2.5 micrometers, I mean 400 nanometers and 2.5 micrometers, there is still the good old halogens, but they produce heats. But that's interesting here because halogen, which are used between 400 and 2,500 nanometers, basically they use the same physical theory, that's the one we are using for our thermal illumination, which is 2.7 and 5.3. It's just that for halogen, the temperature of the filament, it's about 3000 or even more Kelvin, so that it emits pretty well between 400 and 2500 nanometers. But then if you go with a lower temperature, and this is what happens here, if you could use a halogen with a lower temperature somehow, then you will start to emit better in the thermal infrared between 2.7 and 5.3. That's why here, our thermal illumination, it is somehow the same theory, I would say, as halogen, but at 650 Celsius only.
Okay. Do we have any experience with drones? And do we mount these cameras to drones to inspect plants or cultivated fields? So this might be a good time to introduce behind you. We do have the AFX camera. So that is an airborne camera designed for mounting to a drone. So Mathieu, you can talk a little bit about what you're holding there. Okay.
So this one, it's not a mock-up actually, it's a real one. It is a AFX17. So we have AFX10 and AFX17. So the AFX17, it is one of our latest baby, I could say. So it includes inside an FX10 or FX17. So here it is an FX17. Also a GNSS IMU unit to record the position, like this. And also a card, a kind of computer inside, like to record everything like the data. So all in one, like this. The payload which is required, if I recall well, for the AFX17 is 2.5 kilos, I think.
A little less. I think it's about 2.3.
Yeah,
for the 17.
2.1 for the FX10. Yeah, it's about that. Yeah. So this is what we have, but we don't have it for the FX50.
Right, and you talked about that a little bit with the remote sensing for the FX50, that it is a little more difficult, and it does weigh a bit more at 7 kilos. So that makes sense.
Just one thing, if you are really interested by the AFX camera, we also had a webinar a few months ago about the AFX, and here I really encourage you to look at it, because Yuka, who is our really specialist about AFX camera, made one, and then you will find a lot of information there about it.
Yeah, so you can find that on our website, and you can also reach out to us directly, and we'd be happy to share that link with you as well. Do you see any applications in food? And I'm not sure if this question is for this camera in particular, but or Specim in general, but we do have lots of applications in food for foreign object detection and meat inspection, things like that, for the FX10 and the FX17. Do you see any applications for the food industry with the FX50?
Well, not really. We start to have some requests for the FX50 for, let's say, agriculture or transformation of agriculture product to become food, but directly on transform food like contaminant, things like this, I'm not aware of any of those.
Okay. And we also did a similar webinar earlier this summer on food applications. So we could also share that link. That's one of the presentations you talked about earlier on this webinar. So we can send that link to our YouTube channel so you can see the food application webinar. What is the sensor in the mid-wave infrared camera, the FX50?
INSB. It's an INSB.
How about your time to market? I know roughly the NIR is a major tech in the area of sorting. Also, some companies mentioned they can also detect black plastics. So this is a product. This has already been launched about a year ago. So we're producing these in production, and they are ready to go.
It is ready to go. Yeah.
Again, with the illumination, so it's another question on the illumination. I think we touched on that, and about how it heats up the sample. I think that's an important note that you made with the art example that you gave. that it only heats it up a few degrees as long as you're scanning at a consistent rate.
Yeah, and think about it. It was only 20 centimeter per second, which is slow actually. 20 centimeter per second is not fast. Typically, when you are working with a sorting plant with a conveyor and you need to sort like plastic or waste, it's about 2-3 meters per second. So basically, it doesn't heat up your samples.
Can you envision this being a field-based system for scanning cores or comparable materials in a non-industrial setting? Can it be ruggedized?
You mean like scanning on the field?
Yes.
Well, it's what I was showing. So it could be used on the field as well. The only constraint, it is the illumination. So it could be used.
Right.
It was a bit the image that I was showing, like when we were on our parking place. You remember the image I was showing? It could be used, but again, if you are working in the reflection mode, you need to be aware that the illumination might be a problem. So for this kind of agriculture application, FX50, I don't really see a high potential. But if you are working on the field for emission purpose, emission, it could be like a hot flame, it could be hot whatever, something which is emitting, then it's another story. The camera could be used, and then the signal will be much better because the distance between the sample and the camera will not be as long as the full atmosphere, which is absorbing everything. There will be only a little bit of absorption, and then it could be used. And this camera could be used for that purpose. For your information, the camera could be put as well in a casing if it is needed.
Right. Yeah, that's an important part too. When you talk about classifying different materials, and you showed the one slide where you could see different types of plastic, and then they show up as different colors because they're classified. Yeah. How does that compare to AI-based vision and machine learning?
Okay, so here I was using, as I was explaining, normalization, Savitsky-Golay, then derivative, and PLSDA. So basically, I was putting few calibration samples. I was pointing out some spectrum, and then those spectrums, they were used as spectral library, and then with a partially square method, basically there was some possibility to make some statistical identification. This is what I've been using. But there are some other methods. I know some people like to use deep learning, neural networks, things like this. It's possible to do it. It's just that I did not do it for this application. But it's a possibility.
Okay. Is it possible to use the FX50 to see components of liquid mixtures?
I haven't tried, but my little finger is telling me that water might be the problem, because water will absorb most of the wavelength. So if you are looking with a transmission setup, which is typical for looking at the liquid, I'm afraid it will be dark.
What do we do for the range between 1700 and 2700 nanometers? It seems to be a gap in what we discussed today, but we do have a solution for that.
We do have the SVIR camera. The SVIR camera is actually covering the spectral range between 1000 and 2500 nanometers. Then the gap is not as big anymore, but there is a small gap between 2500 and 2700 nanometers. There, okay, we don't have anything, but it's only 200 nanometers out of the full range.
We're getting a lot of feedback too with different applications. It seems that vegetation, life science, remote sensing, a lot of agriculture. So those seem to be the other application fields that were not in our poll. So that's great to get that feedback from everyone as well.
Okay.
My application is entomology and biodiversity, so environmental monitoring. I would be very interested in coming to Finland to carry out a feasibility study. Can we arrange the camera and illuminator in specular condition, plus or minus 45 degree? Do we have the possibility to record both co and depolarized images? Do we have mid-wave infrared polarizers? So a lot there. One, yes, we can always take samples and welcome anyone to come to do the samples as well. But I guess the main question there is, can we use co and depolarized imaging with mid-wave infrared polarizers?
Okay, so there are many things here. First of all, can you come to Finland? Well, at the date of today, it depends on Corona.
It depends where you're coming from.
Because I must tell you that right now, if you look at the Finnish map where we're allowed to travel, it is only Latvia, Estonia, and Vatican. That's it. Except of that, now the Finnish border is kind of closed. There is a need for quarantine. So that's the first thing. When this is over, then, of course, people are welcome to come. If, again, as I say, we're not service provider, but then we see there is a potential. If there is a potential, yes, actually, we already made some measurements in a specular fashion, because there was one aspect I did not speak about, especially for the black plastic. For the black plastics, let's say there are two kinds. There are some which are really shiny, and there are some which are a bit scuffed. When they are scuffed, you could work with our illumination in the diffuse mode. There is no problem. You can have a good signal. But when they are not scuffed, then they are really shiny. You don't get any diffuse signal, and then the camera will be blind when you use our illumination in the diffuse mode. But you remember how it looks like. It was two setups next to each other. If you remove one and you put the camera with a 45 degrees, actually you can see specular reflection. And this can be used to solve black plastic when they are shiny. So to answer to your question, yes, we could use this camera in a specular fashion. Then about the polarizer, I don't know. I might exist, but at least at Specim, I'm not aware we are having any one for this spectral range.
Yeah, that would be great to learn. What is the range of the illumination in terms of object height? And is there a tolerance for the height? So how basically can the illumination work well with an object that are 10 millimeters high all the way to 50 millimeters high? What's kind of the focal tolerance there?
Okay, so then I will ask our moderator, Harry, is it possible to have the presentation back? Let's see if we cannot have, yes, it's possible to have the presentation back. And then it takes a few seconds, and I will go back to the slide about the illumination. I cannot go faster than that. I'm sorry. I'm getting there soon. Now I'm talking with the scanner. Here we are talking soon. Illumination. All right, here we are. And then I use the pen. Basically, it has been designed so that the distance between here and the sample is about 5 centimeters. 5 centimeters when the distance between the two units here, it's about 2 centimeters. So when there is 2 centimeters between the units, then the optimal position to have the focal plane for the illumination, we could say that way, it's about 5 centimeters away from the bottom of the illumination. Having said that, we made some tests. If you increase here the space, then you can increase the distance here as well. And I made some tests, and there is no significant drop in the intensity of the signal if the distance here is going from 5 to about 12 centimeters. Of course, here you need to increase the distance here. But down to 12 centimeters, it's okay, and you can still have a really good signal without changing your integration time. So it could work that way.
Okay, yeah. Which wavelengths does the FX17 cover? So that was 900 to 1700 nanometers. Also can cover that range in the SWIR camera, which covers 1000 to 2500 nanometers. There's also the Phoenix camera, which does the full visible to SWIR range, 400 to 2500 nanometers. So if any of those wavelengths are what you're interested in, any of those cameras could be the right solution. Do we work on ultra-spectral sensors or cameras?
Do we work on?
Ultra-spectral sensors or cameras? Not sure.
No. I don't know what is ultra-spectral sensor. I don't know what is that.
So I think that means just how we do the diffraction. So we use a 2-dimensional monochrome camera, as our detector, and we're using transmissive grating to actually disperse the light. So ultraspectral sensors, meaning they can detect different wavelengths. Maybe that's what they're referring to. But that's how our systems work. It's a diffractive grating and a monochrome 2D sensor, and that's how we get our spatial and spectral information that way. Let me find another one. Analysis of liquid mixtures. We talked about a little bit about that. Is there a similar webinar for the AFX series planned? And not so much a Q&A like this one, but there is a pre-recorded webinar about the AFX that was launched in January or February of this year. So it's a very recent webinar. So we can send the link for that for sure. What is the impact of moisture on the surface of an image material? So for wet samples.
It is massive because the water absorbs almost all the wavelengths between 2.7 and 5.3 micrometers. That means that basically it may, if the moisture is high, it will make your camera blind. So we are used to say when you are using this camera, sample should be as dry as possible.
How about detection of multi-layer packaging or contaminated multi-material plastic?
Well, we have tried. It was not really convincing.
So I think that's about it for the questions. The link for the AFX webinar is there.
Okay.
Petri, thank you. Wrote in the IBIS is an ultraspectral. It has more than 1,000 bands. So that might answer that last question. So thank you for that. Can the FX50 be used for textile sorting?
That's a good question. Textile sorting is quite a hot topic, and think about it. Textile, it can have different colors, different type of materials. There are cotton, there are nylon, there are different type of material. If they are not black, the FX17 can really separate the different type of material. If they are black, 90% of the time, actually the dyeing solution is not based on carbon to be black. So that means the FX17 could still separate them because in the NIR, they are not black. The problem starts when the dyeing solution is made of black carbon. So then here, FX17 could be one solution. FX50 could be one solution.
Right, the FX50.
Yep.
Are we going to develop a long-wave infrared Phoenix camera? So is that something that we would consider doing? I guess we do have long-wave infrared cameras. So I guess you could talk about that for a second. But combining that with a Phoenix for the entire spectral range.
Or if they were meaning like between MWIR and long-wave infrared together, no, this is not planned.
But we do have solutions in the long-wave infrared from 8 to 15?
8 to 12.
8 to 12 micron. The FX50 illumination says filament temperature is 650 degrees C. Yeah. Secures 1,000 millimeter around the lighting as a worker's safety distance. So is it dangerous?
Well, it's dangerous if you put your hand underneath. Yes, you will burn your hand. But it happens the same if you have a halogen lamp. If you take the lamp like this, you will burn your hand as well. So, right. Yeah, it's dangerous if you really touch it. I would say in a not really clever way. But it's the same for a lot of other things, like, as I say, halogens or things like this. Yep. I would say it's really dangerous, but you have to be a bit careful.
Understood. Based on the polling, we're seeing recycling at 5%, food applications at 8%, geology at 13%, and other at 72%. And again, the other really, it captured a lot of agriculture, medical, biological, surface studies, and remote sensing. So that's interesting that's a bulk of the audience right now. That's about it for the questions. We're running, I think, just about to an hour at this point. So if you have any other questions, feel free to reach out to Mathieu or I directly. We can give our contact information at the end of the webinar. Please reach out. We're happy to help. We're happy to answer any further questions you may have that you may not have asked here. Please feel free to share the recording with your friends and colleagues, anyone who you think would find this interesting. And thank you, Mathieu, for taking the time to present this. It was a very, very good presentation, very general, hyperspectral, and then more specific into the mid-wave infrared applications. So a nice overview, and thank you very much for everyone who joined. Please stay safe out there, and enjoy the rest of your day.
Thank you very much. Bye-bye.